Hello everybody and welcome back. As we progress through the last part of our analysis of organic molecule structure, we're going to spend some time talking about conjugation as a structural aspect of molecules and UV spectroscopy as a way to detect that. So as we have discussed organic molecular structure analysis, we've talked about mass spec, we've talked about infrared spec to tell us what functional groups are present, nuclear magnetic resonance or NMR spectroscopy to tell us what the CH framework is and to help us assemble the molecule. Ultraviolet spectroscopy really only tells us if conjugated systems are present, so a little bit more limited. However, first we need to talk about what is a conjugated system. Conjugation involves the alternating structure where we have a single bond and a double bond alternating throughout a molecule. And really what we're talking about is overlapping pi bonds or p orbitals from the atomic standpoint, allowing electrons to flow between a collection of atoms through the molecule. So the easy way to think about it is that conjugation occurs when two double bonds are separated by one single bond. And so in the case of 1,3-butadiene here, we have a double bond, then a single bond, then a double bond. This is a conjugated system with two double bonds, two pi bonds. On the other hand, we have 1,4-pentadiene. We can still see that we have two double bonds, but they're separated by an sp3 hybridized carbon, or two single bonds, if you want to think about it that way. This is a non-conjugated system. And the reality here, the practical aspect of this, is that if we were to treat 1,4-pentadiene with any of a number of reagents that we've learned about in our discussion of alkene chemistry, we could think about the alkene here between carbons 1 and 2 and the alkene between carbons 4 and 5 as reacting as two separate sites in the molecule. So for instance, if we were to treat this molecule with HBr, we would expect to get a bromine added to carbon 2 and a bromine added to carbon 4 in our standard Markovnikov additions to both alkenes. However, as we'll see in a few slides, if we were to treat something like 1,3-butadiene with HBr, we'll get a product that we may not have expected due to the unique overlap or proximity of these two pi bonding systems to one another. We'll get to that in a moment. So conjugation occurs when two pi systems are separated by only a single bond. So we have a collection of sp2 hybridized carbons. It doesn't all have to be carbons. So we saw here 1,3-butadiene. We can see over here a collection of different scenarios where we do have conjugation, although we're involving some different structures. In the case of this first molecule on the left, we have a nitrogen with a lone pair of electrons. So that extra pair of electrons separated here from a double bond, separated from another double bond, separated from another double bond. Similarly in furan, we have two carbon-carbon double bonds that we can imagine. We also have a pair of electrons on the oxygen. And here on the right, we have a carbanion with a pair of electrons shown completing that conjugated system. Benzene is a cyclic conjugated molecule, and we'll see in a later chapter that this particular scenario is considered aromatic, and we'll talk about what that means as a particularly stable version of a conjugated system. And taken from biology, many steroids, this is progesterone, have a conjugated region, and that's outlined here in pink, where we have a carbonyl group in this ketone separated by one bond from this alkene. So a so-called enone, where we have conjugation here between the alkene and the ketone. Conjugation is common in nature in molecules that are colored. As we'll see when we talk about UV spec, conjugated systems absorb light in the ultraviolet region, but extensively conjugated systems have that wavelength of absorption shifted up a little bit into the purple and blue, the sort of violet end of the visible spectrum. When we absorb those Cooler colors of light, of course, we then see reflected to us more of the warm colors. So things in nature that are red and orange and sometimes yellow are often the result of conjugated molecules. The one shown here is lycopene, which is one of the primary components that makes tomatoes red. And you can see outlined in pink all of these alternating pi bonding systems. Industry has made extensive use of these, creating synthetic conjugated systems. So this one, if you follow through, has alternating not just single bonds with double bonds, but also with triple bonds. Anytime we have this pi bonding system and sp2 hybridization, I should say a free p orbital on the atom, we can get conjugation. So if you follow the train through, this entire molecule is conjugated. Likewise in electronics and color development and lots of different technical applications, we can see some really novel structures being built. Some of them provide useful insights into these technologies, and some end up not being very practical. Nature has further examples for us in conjugation in terms of hemoglobin and chlorophyll. These two, of course, are molecules in nature that complex metal ions. We can see in hemoglobin the iron complexed by a series of nitrogens, and in chlorophyll it's a magnesium center. But if you follow around the outside of these molecules, you can see definitely these conjugated systems of alternating single and double bonding. That's true around chlorophyll as well. These molecules, of course, have different structures. They absorb light a little bit differently, and so we get hemoglobin appearing to sort of a darkish reddish color, whereas chlorophyll, of course, appears a little bit more into the greens. Industry has also taken some cues from nature and created dyes that are conjugated. So copper phthalocyanine is one where we have now a copper center, but in a ring that's conjugated, sort of gives us vestiges of that hemoglobin or chlorophyll sort of a structure. So besides the fact that they tend to be nicely colored if they're extensively conjugated, why do we care about these molecules? Well, conjugated systems are particularly stable, and we'll see this even more so later on when we talk about aromatic systems, but conjugated systems are especially stable, and this is based on the idea that we have overlapping orbitals. So we can consider this from two different perspectives. Our first perspective is just valence bond theory, looking at each individual atom and recalling that hybrid atoms that are more S-like have shorter and stronger bonds than those that are more P-like. And so when we talk about having an alkane, we have overlapping sp3 orbitals in between atoms. Whereas if we talk about having an alkene, or particularly here a pair of alkenes that are in a conjugated system, all of the bonds, including this middle bond, are formed by an overlap of sp2 orbitals. And you can prove that to yourself if you draw out the bonding for any one of these carbons. They're connected to three separate groups. So if we look at carbon 2 in particular here, we have a bond to the CH2 group at the end, we have a bond to hydrogen, and we have a third bond over to the rest of the molecule. Those three groups give us the sp2 hybridization, and the extra electrons here are in a pi bond caused by the overlap of p orbitals from both of these atoms 1 and 2. Since this pink bond here is shown as an overlap of sp2 orbitals, it's a little bit stronger than it would be from the overlap of sp3 orbitals. This is a little bit easier to understand if we consider the molecule as a whole. And that's what molecular orbital theory does for us. Now, I am not going to go extensively into MO theory. There are loads of resources out there if you want to dive deeper. Other courses as you go higher in your chemistry education will dive deeper into MO theory. But suffice to say that molecular orbital theory allows us to consider more than just two atoms at a time. We're not just considering hybridization of one atom compared to the other. We're considering how a collection of atoms would work together. And so the way that we will address molecular orbital theory is to generate MO diagrams, and we will fill in those diagrams here, starting with bonding molecular orbitals. Those are the lower in energy ones that will fill up first, and those will contribute to holding the molecule together or stabilizing the molecule. We'll have anti-bonding molecular orbitals that are the ones higher in energy. If those get filled with electrons, that tends to destabilize the molecule. And we'll keep in mind that each bond still contains 2 electrons. So let's look at a simple example here. If we are just looking at a single alkene, all right, just 2 carbons in an alkene bond. Of course, those carbons are connected to one another in their first connection by a sigma bond or an overlap in the valence bond theory lingo of an sp2 hybrid orbital. That p bond or pi bond is created by the overlap of the p orbital that's unused on each carbon. Recall that p orbitals are so called because they're polar. They have sort of the 2 regions of electron density. And they're color-coded here, red and blue, just so that we can keep track of them. Essentially, what we want to think about is if we're looking at 2 atomic orbitals here on the left, and we're trying to consider those as a molecular orbital system, 2 atomic orbitals going into this system will result in 2 molecular orbitals coming out. These are labeled here as Psi1 and Psi2. The one here in blue is lower in energy, so it's drawn a bit further down on the diagram than the original atomic orbitals. Psi2 here with the star is indicating an anti-bonding molecular orbital. That's drawn to a little bit higher energy level. And so the key thing to remember is that this system, we started with 2 atomic orbitals. We're now ending with 2 molecular orbitals, where we're considering them together. And we have 2 total pi electrons to place into this system. In every case, the lowest energy molecular orbital that you'll see is the one in which all of the atomic orbitals line up with the same polarity. So you can see here the red bits are on the top and the blue bits are on the bottom. The only other way that these 2 orbitals could go together is if we imagined that they were sort of in reverse polarity to one another. There's a little bit of a repulsion, or what's called a node, here in between. This is a higher energy scenario, sort of imagine magnets kind of repelling each other, sort of a simplistic way to look at it. Every orbital holds 2 electrons, like you've learned from Gen Chem on forward. So when we start to place our 2 pi electrons that we have from these 2 carbons, one from each of these carbons, both of them can fit into the bonding molecular orbital. So we have 2 electrons contributing to bonding. We have no electrons left to go into the anti-bonding. And so the alkene is stable based on the sharing of electrons through this Psi1 molecular orbital. Now, if we try to make it more complicated, we start to look at 4 carbons in a row with 2 pi bonds, in other words, a conjugated system. We see a similar arrangement, but we see more possibilities for how those orbitals can line up towards one another. We'll still have a scenario where we have 4 atomic orbitals that we're considering sort of going into this diagram. And so we'll end up now with 4 molecular orbitals coming out of varying energy levels. In this case, 2 of those molecular orbitals will be bonding. They'll be lower in energy. And 2 will be anti-bonding, higher in energy than the original atomic orbitals that we started with. So using the same logic here, we have the lowest energy, or the sort of best case scenario, where all 4 orbitals line up together in the same polarity. And so electrons would be free to flow between all 4 of these formerly atomic orbitals. We have a slightly worse scenario where we have 2 pairs. So this is shown with carbons 1 and 2 lined up in one polarity, and carbons 3 and 4 lined up in the other polarity. That gives us 1 node in between where we have a repulsion between these 2 groups. That's not quite as good as Psi1, but better than it could be. As we progress up, the first anti-bonding molecular orbital, the first one that's higher in energy than we started with, shows us only 1 pair of aligned orbitals, so carbons 2 and 3 here. Carbons 1 and 4 are in the opposite polarity, so this introduces 2 nodes, or 2 points of instability. And then at the top, Psi4 is our worst case scenario where nothing is aligned. All 4 orbitals are repelling one another or in the reverse alignment, reverse polarity. And so we ended up with 3 nodes. This is the worst case. So 4 atomic orbitals go into this little machine, 4 molecular orbital systems come out. 2 below and 2 above that original starting line. Now remember that we had 4 pi electrons to be able to place into these molecular orbital systems. That's 2 each from these 2 double bonds, so 4 electrons total. Just like any other time we've filled orbitals in chemistry, we'll fill them from the lowest position first, the lowest energy. So 2 electrons can fill into this lowest energy molecular orbital, the Psi1. 2 electrons can fill into the Psi2 molecular orbital system, and that leaves nothing to fill into the antibonding nodes. The overlap of these orbitals in this way makes all of the bonds stronger. We're not considering individual pairs of atoms now that are bonded together. We're considering that electrons really can flow across large portions of the molecule. The fact that we have all of our electrons placed into bonding orbitals tells us that, in fact, this is a stable configuration. So what's the practical purpose here? Well, just like we learned in the alkenes chapter, we can do all of those reactions to conjugated alkenes. And so what we have shown here on this slide are 2 different standalone alkenes. In the top box, we have 2-methylpropene. This is just a single alkene bond. If we treat that with HX, we know we go through a carbocation intermediate and we end up with Markovnikov addition of X, so chlorine here, to our molecule. So we've added HX across what used to be the double bond. That same thing happens if we talk about a non-conjugated diene or triene or whatever it might be, where we have isolated double bonds. Each one of these alkenes, because they're not conjugated together, each one of these alkenes would react just the same way as a standalone alkene. And so if we treat with excess HCl, we'd get the exact same kind of Markovnikov addition to each alkene. And so we would get this dichloro molecule where we have chlorines on carbons 2 and 4. Both of those are Markovnikov additions. Now, if we do the same kind of a reaction with a conjugated system, things are just a little bit different. We do get what we would expect, and so this is assuming we only treated with 1 equivalent of HX. We do get what we would expect. We get Markovnikov addition across that double bond, the so-called 1,2 addition. Now, of course, these aren't necessarily carbons 1 and 2 in the real numbering sense. These are carbons 1 and 2 of our 4-carbon conjugated diene system. So this 1,2 and 1,4 nomenclature is sort of relative. Happens to be correct in this case as well. So we can get Markovnikov addition here. And of course, if we continued to treat this molecule with HBr, we could get Markovnikov addition on the other alkene, and that's just fine. But with some frequency, we can get a bromine attached to carbon 4, or maybe now we'd call it carbon 1, in the so-called 1,4 addition. And the question is, well, how in the world does that happen? This is a special scenario that is possible because of the way that these 4 carbons had overlapping pi bonds in the first place. Remember, those orbitals overlapped and allowed for an easy flow of electrons. If we look at the mechanism here on the next slide, here's our original molecule. If we just do the acid treatment part of the HX, we know that H will add to the less substituted carbon in our Markovnikov sort of a situation. And that'll generate a positive charge for us, a carbocation, at the next carbon. So this is our intermediate that we would expect. And if we just went ahead and allowed that nucleophilic bromine to attack, we would get the 1,2 addition product that we might expect from a traditional alkene reaction. However, notice that we now have a carbocation with nearby an adjacent source of electrons. So we can get a movement of electrons here where these pi electrons could move over to create a double bond between carbons 2 and 3, leaving the positive charge now on the end of the molecule, like this. Now, of course, this is less stable. Having the primary carbocation compared to a secondary carbocation is less stable, but in both cases, these are so-called allylic carbocations in that they are one step away from a double bond. And so this isn't a sort of traditional primary, it's a primary allylic, or over here, a secondary allylic carbocation. In the case where this is the intermediate that has formed, or rather when the intermediate is in this form, if the nucleophile attacks, this is how we get the 1,4 addition. Notice that the double bond has moved. We didn't originally have a double bond between carbons 2 and 3 in the starting material. We do now because of that movement of electrons in the intermediate step. Because this is the less stable intermediate, we do get a lesser amount of that material here. And it turns out that we can tweak this. So by controlling the reaction conditions, we can bias whether we favor the 1,2 addition product or the 1,4 addition product. And it turns out that that really comes down to temperature. Because the 1,4 addition product required a rearrangement, that rearrangement requires additional energy. And we can read out energy as temperature. So if we keep the material at low temperature, the 1,2 product predominates. It's faster, it doesn't require that intermediate step, and so we get more of the reaction going in the 1,2 direction at low temperature. This is the so-called kinetic product. If, however, we're at higher temperature, now we can allow that rearrangement to occur. We can then generate more of the 1,4 product, or what would be called here the thermodynamic product. Because we're at higher temperature, though, this is also reversible. And so it's a little bit of a tricky balance between the two. If we were to look at a reaction diagram, it might look something like this. Our starting materials have a certain amount of energy. We go through that initial step to form our intermediate carbocation. And then at low temperature, we would just follow the green line here to form this low energy 1,2 product. If we have enough energy, a higher temperature, to get over this secondary reaction pathway, the pink one, we can form the 1,4 adduct. If we're not careful, the reversibility comes here that we could push back over this bump and get back here, and then potentially go down the other path. So we have two products here. The take-home message is that at low temperature, we tend to form the 1,2 product. At higher temperature, we tend to form the 1,4 product. And those are called, respectively, the kinetic and the thermodynamic products. There is another sort of nifty reaction that occurs when we have conjugated systems. And this is called the Diels-Alder reaction. There are several of these types of reactions out there. We're going to focus in on this one. This is the reaction of a conjugated diene. So as we see here on the left, this is a 4-carbon conjugated diene with something else that has some pi electrons. And shown here as an alkene. We're going to see in a couple of slides that there are some other options. But what this allows us to do is to form a cyclic molecule. It's one of only a few ways we have in the test tube to form a ring. And so this is a really cool one to remember. It has been shown to make 2 carbon-carbon bonds at once. We have this simultaneous reaction across all 6 of these carbons. And it resulted in the Nobel Prize to a couple of scientists called Diels and Alder. And before we get to the details here, I just want to introduce the terminology. We have the diene, which is our at least 4-carbon system here. So a diene would be 4 carbons with 2 alternating double bonds. This particular one is shown with all hydrogens, but they don't have to be. And we have the so-called dienephile. This is the 2-carbon system with extra electron density that will react with the diene. We get this cyclization that results in a cyclohexene molecule. Just as a quick side note, these are Professors Diels and Alder, awarded the 1950 Nobel Prize in Chemistry for their discovery and development of this synthesis. So the Nobel Prize website, by the way, is a great resource to look at scientific history. This link will take you specifically to the 1950 page on chemistry, but There's lots of other interesting stuff on the site if you'd like to look at it. Back to the reaction. What we can think about here in terms of the way that this works is this simultaneous movement of electrons around this 6-carbon system. So imagine that the pi electrons from the dienophile will react with carbon 1 of this diene system. At the same time, the 1,2 double bond gets pushed to the 2,3 position. That prompts the electrons in the 3,4 double bond to get pushed out to the other carbon of the dienophile, which would be electron deficient after that first reaction started to occur. This all seems to happen very, very quickly, or as much as we can tell, sort of simultaneously. What we end up with now is a double bond having been formed between the original carbons 2 and 3 of the diene and new sigma bonds between the ends of the conjugated diene system and the 2 carbons of the dienophile. There are some characteristics we have to consider, both in terms of the diene and the dienophile. The diene itself has to be able to form what's called this S-cis configuration or conformation. Of course, the bond between carbons 2 and 3 is a single bond, and so we can imagine it rotating. However, we need to be able to form this sort of C shape here in order to have the right geometry to form that ring. So in a small, simple diene like this one, of course, C2-C3 bond can rotate to give us this sort of S-trans configuration, S for sigma bond. So this sort of trans configuration, this would not be reactive in a Diels-Alder reaction. However, since it can easily rotate back into the S-cis configuration, this molecule would work. And we're seeing down here below why that's true. If we had a reaction, or sorry, a diene in which the molecule was locked into the S-trans configuration, that diene will not react. So a couple of ways in which that could happen is if we had some sort of a ring structure that was stabilizing this thing. So here's a case where we have conjugated diene. By virtue of being locked into these rings, it's stuck in a trans configuration, an S-trans configuration. This would not form a Diels-Alder product. Likewise, if carbons 1 and 4 of our diene are substituted with bulky groups, and here it's shown as a methyl, certainly anything larger would be a bigger problem. The steric interaction here, the steric strain of these groups running into one another would favor this molecule adopting an S-trans configuration rather than the S-cis configuration. And so this molecule would not react very well. If the methyl groups were in the other positions up here, straight up and straight down, so that they didn't interact with each other, then we would have more success in using this as a Diels-Alder diene. The dienophile also has some particulars. They are most reactive in this kind of mechanism when they have electron withdrawing groups attached. So why would that be the case? Well, remember, part of our reaction mechanism involves that standalone dienophile, that double bond, one of those carbons, accepting some electrons. And so if we have something attached that can polarize it to make one of those carbons a little bit positive, that will help the case. So shown here is ethylene, which is actually not reactive in a Diels-Alder reaction. But if we attach some electron withdrawing groups, whether it's an aldehyde here or an ester, we attach a nitrile group, any number of different options over here, those will help improve the reactivity. We also have a couple of materials that are used commonly in these reactions, benzoquinone and maleic anhydride, or really any number of anhydrides would do this, but we have our 2 carbons of our dienophile now with strongly electron withdrawing groups attached to them. And that makes those carbons quite reactive. The one in the box over here is showing an alkyne. You can think about an alkyne here as having, the necessary pi bonding electrons to do the reaction and another set. And so when we see an alkyne react in this way, we'll do the mechanism the same way that we've seen for an alkene, but we'll end up with still another pi bond between the two carbons of the dienophile. So stereochemistry is a consideration to talk about, and then we'll look at some examples. Cis-trans stereochemistry is retained. Well, what does that mean? So here is a diene in its S-cis configuration. Here is a reactive dienophile, has this electron withdrawing group attached. Notice here that the ester group and the methyl group are on the same side of this starting material. So this is a Z configuration alkene. When this reaction occurs, we get cyclization between these four and these two carbons. Our ring will be here. We'll end up with a double bond between original carbons 2 and 3 of our diene. That's shown here. Notice that our ester group and our methyl are on the same side of the ring, right? The stereochemistry is retained. They're on the same side of the starting alkene. They will end up on the same side of the ring, in this case, both drawn away from us. Likewise, down below, if we started with the E form of that same molecule, we have our 4 carbons here and 2 carbons here forming our ring. Now our ester and our methyl group are on opposite sides of the starting alkene. They will end up on opposite sides of the ring-shaped product. One back, one forward. In some cases, what we'll end up forming here is a 2-ringed system. And you'll see an example in the textbook about how this works. But basically, this is a scenario where we would have had a ring-shaped diene. So imagine a cyclohexadiene, for instance, forming these original, I guess this is 5 carbons, the cyclopentadiene forming these 5 carbons. This would have been our diene, and then these two would have been our dienophile. In that case, when that happens, the bridge carbon will be on the opposite side from where the substituents are. This is all about crowding, okay? The endo substituent is the favored one. If we can put our bulky stuff down here in the pink position, that's more likely to happen than if we have to put it in the blue position because of sterics and interacting with this bridgehead carbon up top. So if we're forming a bicyclic ring product, the endo product is formed. And that's where whatever was attached to your dienophile ends up as far away as possible from the bridgehead. We can see that formed in this way. Here's our cyclopentadiene with carbons 1 and 4 doing the reaction. Here's maleic anhydride, again that activated dienophile. And so we can see that the bridgehead carbon and these 4 carbons were in the original molecule right here. The dienophile brings in the other 2 carbons here, and the bulk of the maleic anhydride is shown going down away from this ring with little hydrogens sticking up in the upward position. This is the so-called endo product. The reverse of that would have been with the bulk of the maleic anhydride being drawn in that upward position and the hydrogens being down. You can sort of hopefully see the steric strain that occurs between this bridgehead bulk up here and the bulk of the maleic anhydride molecule over here. So the endo product is formed, the exo product is not. You'll see lots of examples of Diels-Alder reactions. The key thing to remember as we go back and we look at what a Diels-Alder really looks like is that we want to identify which one of these is the diene and which is the dienophile. And so all you want to do is isolate that system and that system. And whatever else is attached everywhere else, that's fine. But you want to keep those 2 things in mind. So identify the right pieces. And then the reaction that you're talking about is the reaction where we have a cyclization. So these electrons go to form a double bond. These electrons connect the molecules, and these electrons connect the molecules. And so your product would look like this with that double bond here. And whatever else was attached to carbons 1, 2, 3, and 4 over here, carbons 1 and 2 over here, those things stay attached wherever they were. The alkyne situation that I mentioned with that one example, if our dienophile was a triple bond, then that extra bond that didn't react will still be there. And again, whatever else had been attached will stay attached. So don't get too caught up in complicated structures here. It really boils down to identifying which 6 carbons will be part of your final product and going from there. Now, there's another sort of aspect to this chapter that we can talk about, and that is the idea of diene polymers. So we don't cover a tremendous amount about polymers. There are entire courses that cover all the intricacies of polymer chemistry. But suffice to say that rubber is a diene polymer. So here shown is isoprene. You may have heard of lots of these prenes, so isoprene and neoprene and lots of other ones. We'll see a couple of those. But what we have here in pink is just a radical initiator to start the process, but isoprene itself is a modified 1,3-butadiene, so a 2-methyl group attached there. And what we end up with is this situation where we have sort of a conjugated system, if you want to think about it that way, being formed sort of between 2 molecules. This can form natural rubber if the assembly is in the Z form, and so we end up with this kind of a structure. Can form gutta percha if it's formed in the E form, so the same chemistry but an opposite stereochemistry there on those alkenes, and it's a different polymer with different properties. Similarly, if we look at neoprene, which you may hear about in terms of diving suits, that's an example of, again, a differently modified 1,3-butadiene with a chlorine group now instead of a methyl. And so we end up with the same kind of chemistry, forming these long chains with chlorines decorating, every so often here in this repeating pattern. Polymers like this form long chains pretty easily based on the flow of electrons, as we've just described, from molecule to molecule. But they're not particularly useful unless they are cross-linked to one another. So there's a process that you may hear about, and I just lifted this image from Wikipedia, but a process you may hear about called vulcanization. Vulcanization uses sulfurs to connect between 2 positions on 2 separate polymer molecules. So the blue molecule and the green molecule would be 2 separate pieces of polymer that have been cross-linked together. This is an example of industrial cross-linking. Biology cross-links things all the time for stability, oftentimes also using sulfurs, so cysteine bridges and things like that in your biochem class later on. How do we detect conjugation? Well, just quickly here at the end, we have the ability to use ultraviolet light. So we have already talked in other discussions about infrared spectroscopy, where we're using infrared spectrum to detect functional groups and their bending and stretching. UV spectroscopy, as the name suggests, uses ultraviolet light. So we're in the 200 to 400 nanometer range over here. And basically what UV light does here is that it absorbs into double bonds. So it's absorbing in that the electrons in those double bonds are being excited to a higher orbital. So where IR radiation caused the bonds to stretch and bend, UV radiation causes these electrons to move up to a higher excited state. And so whether we talk about it in terms of valence bond theory or molecular orbital theory, we're talking about 2 electrons per bond. We can talk about exciting the highest electron of those to the next higher energy level. And so if we look at a molecular orbital diagram for a 4-carbon system, this would be our 1,3-butadiene, for instance. We've got 4 atomic p orbitals, each of which contains 1 electron. If we model those into 4 molecular orbitals, again, we get 2 bonding orbitals lower in energy and 2 anti-bonding orbitals higher in energy. We place those 4 electrons into their ground state configuration. That's as low an energy level as possible. We would get 2 electrons pairing up in the lowest energy orbital and 2 in the next one up. This next one up, labeled here as psi 2, is our highest occupied molecular orbital, or abbreviated as HOMO, highest occupied molecular orbital. The next one up, the first empty one, is our lowest unoccupied molecular orbital, or LUMO. So when we talk about irradiating this with UV light, all we're talking about doing is providing enough energy for one of the electrons in the highest occupied molecular orbital to get excited up to a position in the lowest unoccupied molecular orbital. We're providing enough energy to do this HOMO to LUMO transition. Now, without getting too deep in the weeds here, the more conjugated the system is, of course, you'll have more atoms listed here on the left. You'll have more molecular orbitals stacked up here in our MO diagram, and the spacing between these two positions will differ depending on the molecule. And the spacing then, since it's indicative of energy level, the spacing will dictate how much energy we require to jump to excite an electron from the HOMO position to the LUMO position. And so that's a long way of saying that the amount of energy required here depends on the structure of the molecule. Molecules that are not very conjugated, so here's 1,3-butadiene, will absorb light in one part of the spectrum. And so we see here a trace across that UV region, 200 to 400 nanometers. And we see that it has a lambda max of 217 nanometers. If we were trying to measure, say, the concentration of 1,3-butadiene in a solution, we could use this. We could generate a standard curve measuring absorption at 217, and we would be sort of specifically, or at least selectively, looking at this molecule, this structure. We can do the same sorts of calculations that you would have done in Gen Chem, probably using Beer's law, where absorbance depends on the particular absorptivity of the molecule, the path length of the sample cell, and the concentration of the material in there. And so we could make standard curves, and we can measure the concentration related to absorbance. We can figure out all of this stuff. The more conjugated a molecule is, the wavelength will change. And so if we look here at just the different sort of examples of conjugated molecules that we could imagine, this is a 1,3-butadiene that's modified. So this would have been the monomer for our isoprene that we saw in our polymers chart a little bit ago. Whereas 1,3-butadiene absorbed at 217, this 2-methyl version absorbs at 220. Pretty similar. Now, if we look at the same 4-carbon conjugated system, but now contained in a ring, the electronics are a little bit different. It's still a 4-carbon conjugated system, but it's a little bit different geometry, a little bit different electronics. We see the lambda max shift a little bit. If we go up now to a 6-carbon conjugated system, here we have an alkene, a single bond, another alkene, a single bond, another alkene. All 6 of these carbons are conjugated to one another. We see the absorption go up a little bit higher on the wavelength chart. And similarly, if we go to an 8-carbon system, now we get all 8 of these conjugated. We see the absorption goes up even higher. Different kinds of absorptions. So here's a carbon-carbon double bond conjugated with a carbon-oxygen double bond. So this is sort of similar to that steroid ring that I showed you at the very beginning. This molecule absorbs at a different wavelength. Benzene, our 6-carbon conjugated, in fact, aromatic molecule, absorbs at a different wavelength yet. If you look at your sunscreen bottle in your cupboard, you'll find that sunscreens come in one of 2 different sort of varieties. Some of them are mineral sunscreens. They'll have inorganic stuff in them with like zinc, for instance, or titanium. Those nanoparticles scatter light, and so when light comes down and hits that stuff displayed on your skin, it gets scattered away to protect you, to protect your underlying skin. The other sort of flavor of sunscreen that you'll find are organic sunscreens. And you'll find if you look up the structures of many of those molecules, they'll have some pretty heavily conjugated systems. And the structures of those would depend on which part of the UV wavelength spectrum they're trying to absorb. So you may have heard about UVA and UVB and UVC rays. Those are subsets of that UV range. And of course, then the specific molecule that is in there will absorb UV light at a different wavelength. So oftentimes you'll find a mixture of UV active chemicals in an organic sunscreen. The danger there, of course, is that some people are allergic to those compounds or sensitive to those compounds, and so you have to be a little bit judicious about which ones you choose to use. The last little section here gets into why we see some of these molecules as being colored. So the trace that's shown for you here in this pink square is the UV/visible trace for a molecule called beta-carotene. Beta-carotene you may be familiar with. It's one of the components in carrots and other orange vegetables, and it appears to our eyes to be sort of a reddish orange color. Well, why is that? Well, beta-carotene is extensively conjugated. What I've done for you at the bottom is I've overlaid the visible spectrum where it would sort of pick up here. So the UV range is typically described as 200 to 400 nanometers, and then we get into the violets and blues and greens, and then going into the warmer colors at higher wavelengths. Beta-carotene is so extensively conjugated that, in fact, its absorption spectrum is shifted over into the blue region. So its maximal absorption is at 455, but you can see there's significant absorption across all of this blue, green, purple sort of region. So when you look at a carrot, for instance, under white light, normal, full spectrum light, all of those wavelengths of light hit the beta-carotene molecule. The blues and purples and greens are absorbed. And so what's left to reflect back to our eyes is this part of the spectrum over here, the yellows and the reds and the oranges. And so molecules like that, like beta-carotene, like lycopene that I showed you earlier, those extensively conjugated molecules oftentimes to us look like they are emitting some warm color, reflecting some warm colors to our eyes. Now actually in our eyes we have some molecules that are involved in receiving dim light signals. And those are, well, we can't see UV light directly. Those molecules are conjugated. And so they are absorbing and reacting to some of the UV or at least UV proximal wavelengths. So one of them is called rhodopsin, which actually is a protein opsin that's connected here to this organic molecule. This double bond starts off in a cis configuration, which if you remember your alkene stuff, the cis configuration is the higher energy scenario. So this is sort of a compressed spring, if you will. When light hits it, particularly light that would be absorbed by this conjugated system, these electrons temporarily can rearrange and the molecule can spring out into a trans kind of a setup. This is a change in the molecular shape, which triggers a little impulse through the optic nerve and gives us that sensation of vision or of a stimulus from this molecule. So really interesting stuff happening in the chemistry of color vision and even dim light vision here. There are a couple other applications of UV spec I want to point out. So I'm a biochemist, and so I'm really interested in the way that chemistry and biology intersect. I've put up a admittedly grainy picture here for you, but of the 4 DNA bases. And you can see hopefully now after our discussion that these are all conjugated. So we have double bonds between carbons and other carbons and oxygens and nitrogens, but we have these extensively conjugated systems in all 4 of our DNA bases. This leads to the idea that we can quantify nucleic acids based on their absorption of light in that UV region. Typically, absorption of 260 nanometer wavelength is used to quantify DNA and RNA. Similarly, I don't have pictures on the slide, but similarly, proteins, several of the amino acids are conjugated, and so we can see absorption of proteins at a slightly higher wavelength, typically used as around 280. And so in a biochemistry lab, you might assess purity of a sample, or you might assess identity of a sample based on the absorption ratio between the A260 and A280. We also have been able to generate lots and lots and lots of synthetic dyes that are conjugated. Some of them are absorb certain wavelengths of light. Some of them, many of them are fluorescent, and so they absorb one wavelength and emit a different one. There are loads of colored and fluorescent dyes that have been developed in all sorts of ways. You can look at those online. A couple of cool examples from biology and biochemistry would be in UV fluorescent microscopy. So we have a dye here called FITSI. It stands for fluorescein isothiocyanate. And so we can sort of see the structure of this. You can see this extensive conjugation using multiple different heteroatoms. This is one of the fluorescent dyes that's often used to label things. And so in this particular picture, it's labeling what looks like probably microtubules here. And then we have another dye that's commonly used called DAPI. You can see its structure here. You can see the extensive conjugation between carbons and nitrogens, and that is frequently used to stain other molecules. And so here's a fluorescence micrograph. These colors are all false colors. The software would assign, whichever color you chose, and so this one's using a blue color to indicate DAPI staining, a green color to indicate FITSI staining, and a red color to indicate a third dye that was used in the sample prep. But these molecules all absorb at different wavelengths because they have different structures and different degrees of conjugation involving different atoms. And so we can visualize them all in the same sample at the same time by scanning across a wavelength range. And then using the computer here to assign some colors that make the pictures really look great in a publication. So as we wrap up here, our important concepts are the idea of dienes and why they're important, why conjugation provides stability, that discussion of atomic versus molecular ways of thinking about the electrons, the addition reactions between 1,2 and 1,4, or the so-called kinetic and thermodynamic reactions. Pay attention to the temperatures when you're looking at problems. If it talks about something being added with heat or added at a low temperature, you'll be favoring one or the other of those two mechanisms. You should be able to draw out the mechanism and the intermediate and explain why the 1,4 product is even possible. And then finally, the Diels-Alder reaction. I showed you a bunch of dienes and a bunch of dienophiles. You should practice with those just to make sure that you understand how they work, paying special attention to the stereochemistry of it, the sterics of those molecules, and how the products are going to look when they're all done. And then at the end, so not a typo here, a sort of separate number 1, the concept of UV spectroscopy. It's not nearly as wide-ranging of a technique as IR or NMR, but when we're trying to detect conjugated molecules, it's a really easy, very low cost, very accessible way to do it. And we can use that to quantify things, as I mentioned there with DNA and RNA. We can use it in the development of dyes and fluorophores for microscopy and all sorts of practical applications. So this wraps up our discussion of molecular analysis as far as we're going to take it right now. We talked in a different section about mass spec and about IR and about NMR and ultraviolet spec. And so with that, I will say have a great day. Thanks for listening and reach out with any questions. Take care.